Hello, thank you for joining me in the talk on Observability 2.0 using OpenTelemetry. Let me introduce myself first. My name is Przemek Maciołek, and for most of my career, I was enabling organizations to use data efficiently through a process which is commonly known as data science. I founded or worked for several startups and concurrently did PhD in the field of machine learning applied to natural language processing. For the past 6 years, I was focusing on applying this experience into highly efficient network monitoring solution called Collective Sense, which later pivoted into LogSense and was eventually acquired by Sumo Logic in 2019. I live in Krakow and with my family, and you can frequently spot me on the local hills where I facilitate my passion into cycling. Feel free to contact me on LinkedIn, especially if you would like to work on OpenTelemetry yourself, or you want to prove me wrong on some of the items I will be sharing today. First things first though, observability. A broad definition is provided by Jurosz Kuro, where observability is a system that allows to ask and answer questions. Observability might be a new term, but monitoring itself is hardly a new problem. And while there is a common confusion if this is a new thing or just fancy new word for monitoring, Charity Majors comes with a handy definition. And as you can see, the emphasis is on your code, the code you write, change, and ship every day. To me, observability is in a way what DevOps is to operations, a change of mindset in which during development, we already think how to monitor things and how to incorporate it into code. Traditionally, there are three pillars of observability: metrics, logs, and traces. Let's start with metrics first. Metrics can be thought as a numerical time series values that can track anything related to performance, error rates, events, and so on. They excel at providing an overall picture of the system. How many users are currently visiting my website? What is the resource consumption? When is my resource consumption going to become critical? Am I still healthy? Metrics are a great source for indication of a problem, which typically can be later investigated using logs and tracing. I believe you all might know logs very well. Logs are automatically produced and timestamped human-readable documentation of events relevant to a particular computer system. And there's a ton of examples of logs. We have access logs, application logs, audit logs, event logs, transaction logs, debugging logs, error logs, antivirus logs, and many others. Logs are great for troubleshooting problems, though typically there's a significant volume of them, and it makes it hard to tell which of the log record really applies to the investigated problem or to which user action, which becomes even more challenging when service-oriented architectures are considered. And this is where traces come into the picture. This signal is perhaps less popular than the other two. They provide insights into the distributed transaction, frequently seen in SOA or microservices, though traces can be also applied to monolithic applications. Trace is a direct acyclic graph of spans. They provide even more fine granular data on what's going in your system and break each transaction into a sequence of time and causality-oriented operations. For the example purposes, let's discuss a trivial architecture in which a request to service A generates another request to service B, which then does a query on the database. This will be our example distributed transaction. As service A handles the request, with tracing enabled, it measures the time it started and generates a new span, the trace building block. Span contains information about the details, such as the trace ID and span ID, which are auto-generated, start time, duration, information about the errors, instrumentation library, resource, HTTP status codes, other metadata, and so on, which typically is present in the span, but I'm not including in this slide for the brevity purposes. Service A is going to make a call to another service. It creates another span. In this case, this is client span for HTTP post request. This span now includes information about its parent, as we have seen here, which matches the span ID that caused it. As the information about the operation need to include what triggered it, we need to embed this context into the remote call. This is handled through context propagation. In this case, we're injecting a header, trace parent header, using W3C trace context standard. It includes information about the trace ID and span ID, as well as several other properties. Service B then unpacks this context when handling the request from the header and generates another span, which now attributes the parent span ID and trace ID to the information provided in the context when handling the HTTP post operation. The last span runs a query on the database. While it refers to the database, it is not actually instrumented on the database side, but rather by the instrumentation library inside service B. However, for clarity, we can still mark it as the database call, which is presenting with this color here. The whole sequence of operations can be then presented in a time domain using trace view. Each of the spans is presented according to its sequence and duration. As we can see in this example, the overall request time here is mostly depending on the query execution time, the last spans in this sequence. However, this not always needs to be the case. Let's look at another example. Why is there such a long gap between the start type of order span in service B and start of the database call? Is there another call that we might be missing? Or maybe database client needs some time to initialize? Is it latency issue? Tracing allows us to find some interesting insights. Sometimes the reason for a strange situation can be presented in the associated metadata, like response code or error messages, but sometimes traces bring more questions where we might want to use the information or data available in the correlated log and metrics. And this is really when it all comes to play. We wouldn't be able to do the correlation if we cannot tell how the metrics, logs, and traces are related to each other. For metrics as well as logs and traces, we can use information about the resource. Essentially, for example, we can filter relevant data basing on the data coming from the same source. So if they have shared the same instance ID or Kubernetes pod, or maybe ARN cluster as in this example. With OpenTelemetry, we can be sure that the same set of resource attributes will be assigned to each of the signals, which allows or enables the correlation. For logs and traces, we can have additionally ability to correlate data using the trace context. We can inject the trace ID and span ID in the logs. And this allows us to match logs executed during a given span within the transaction and is an extremely powerful capability. As an example, we have a trace view with some spans that generated errors. Please note the red line here. With just one click away, we can check what are the logs associated with this span. As we can see on this example, we have matched logs that indicate the warning message about tiramisu not being available at the automated coffee shop store. And frankly, I love both tiramisu and coffee. Of course, all of that I'm showing is not a new problem, which can be attested even by the number of open source projects many of you probably had a chance to work with. There are multiple initiatives, though most of them focus on providing just single pillar capabilities. And we need all of them for observability. Generally speaking, we can break down the observability architectures into 3 layers. The first one is instrumentation layer. This is about actually generating the data, logs, traces, and spans. This happens through a tightly coupled library that is running on with the service. It can handle manual, automatic, or semi-automatic instrumentation. And with the solutions available just a couple of years ago, you will need to have a separate library for handling each of the signal types. The next layer is collector layer. As typically you want to keep the instrumentation library having minimal footprint on the service you are instrumenting, collector comes handy with providing all sorts of processing capabilities, buffering, handling connections to the backend, and such. It also provides enrichment capability, which attaches metadata about the origin of the data. This helps you to navigate the signals, which can now include information about the source, which I was describing before. Then we have the backend, which stores the data and provides query and visualization capabilities. When you are running some web UI to see what's happening in your system, this is where all those queries go, as you can imagine. There's a lot of moving parts at each layer. And additionally, since there are several instrumentation libraries available for different vendors or open source projects, when you want to switch from one to another, you might encounter a problem, as you might already invested some time in providing the configuration or writing integrations using the API and such. This would changing the library would mean that you need to redo this hard work. So we have some open source initiatives. Two very popular open source initiatives related to tracing, which is probably the hardest signal to get due to context propagation requirements for having API SDKs for each language and so on. Among the most successful were OpenCensus and OpenTracing. Both of them originated at Google. One from Census project, and OpenTracing was based on paper concepts. OpenTracing was perhaps more focused on just providing the API and specification, which was later used by other projects such as Jaeger or Datadog, while OpenCensus provided also implementation and metric capabilities. Since the initiatives shared common goals, a merger happened, and it was announced in May 2019, and that under CNCF governance, a new project, OpenTelemetry, will be developed. The project got a significant backing by many major vendors, and since August 2021, its status was updated to incubating. This was, of course, welcome news, and it had really good coverage in media. And everyone is really happy that finally we have a solution that will solve many of those problems I was discussing before. And what does it mean in terms of the observability architecture? Let me refer to the diagram that I was describing just before, Observability 1.0, and let's look how Observability 2.0 can work. We are not exactly there yet, though very close, and definitely much closer to the chart on the right than the chart on the left. If you recall, for Observability 1.0, all of the stuff required a separate library and agent for each of the observability signals. This is not the case for OpenTelemetry, where pretty much anything except the backend is streamlined and provided by the initiative. There are common libraries for each of the programming languages. There's common collector and such. The vendors can provide their own distributions of each of these components, but eventually they all share the same core code. So we now have a single library that could handle instrumentation, both manual and automatic. And we also have a single collector or agent, which allows to plug in many external data sources and correlate the signals. It also includes a rich set of processors and exporters for both open standards and multiple vendors, though OpenTelemetry encourages to adopt the OTel by the vendors, which is largely happening these days. Now, let's dissect OpenTelemetry and talk about different parts of it and the development process in general. One of the ways initiatives related to OpenTelemetry can be broken down is following. We have specification, where it is defined how to handle things and how components should interact with each other. We have language-specific SDKs, where libraries and APIs are being developed. And we have collector, where, well, agent collector is being developed. Each of the initiatives have an associated SIG, special interest group, where multiple topics, issues, PRs, and such are discussed. SIGs generate outcomes. Specification SIGs generate specifications, which are being later applied to both SDK SIGs and OTC SIGs, and eventually come into specific components. I would like to mention several interesting repositories here. Here, some related to specification. The first one is the specification itself, which includes the guidelines, API, SDK descriptions, and semantic conventions. We also have OTEPs, or enhancements proposals repository, where anything that is a major change or major new initiative is being brought for discussion. And we have Proto. Proto is very handy for understanding what is the model being used for all of the signals. As an example of what is the contents of these repositories, here we have a small excerpt from language library generic design with discussion how to compose it out of API and SDK. Here we have another example. Large part of the specification is related to semantic conventions, which describe how to include information about resources or properties related to given operation or event. For example, I brought here AWS ECS semantic conventions, and this describes how to, for example, name the ARN of the cluster and what are the example values and so on. And we all know that one of the two biggest problems in computer science is naming things. So this largely solves it. OpenTelemetry already covers a number of languages and frameworks. Many of them are actually quite mature, and I believe they could be used on production. For some languages, both manual and automatic instrumentation is available. In the case of the latter, the API calls of popular frameworks are intercepted and a special code is injected, which handles automatic context propagation and span generation. This works for commonly used HTTP client, the server libraries, database clients, message queues, logging libraries for context injection, and many other types of frameworks, depending on the actual instrumentation library. The progress of libraries in general can be tracked using, for example, compliance matrix, where each of them can be checked for support of various capabilities defined in OpenTelemetry specification. There is also OpenTelemetry status page, which includes more details. And now let's see how this all works in practice. I have compiled a very trivial Golang HTTP server. It is using Gorilla Mux for handling the request here, and additionally, when the request is handled, there's one more function being called here. If we would like to add tracing, we just need to add some dependencies, like for example, this imported library, and initialize the tracer, which happens here. There is some boilerplate code behind it, which I do not include here, but it's largely streamlined. Now we can refer to the tracer using this and include the service name, so we can later attribute the spans to a specific service. And in this example, we have two modes of instrumentation. First, we're using a special middleware for Gorilla Mux, which will intercept the request and handle creation of the spans and propagation of the context. I would call it semi-automatic instrumentation, since it simplifies a lot of things, but still some changes in the code are required to make it work, like providing this dependency and including this middleware. Additionally, in GetUser, we have an example of manual instrumentation. We have a good amount of control over it. We set the name to GetUser for the span and include ID attribute, which will include, the ID. For metrics, it's largely the same story. We need to initialize the meter and then refer to it. Here we define some instrument. In this case, it's counter, which has user's rec count name and some description. And here we have an example on how to refer to this counter and actually increase it. I think it's pretty simple. It's a slightly different story for logs. OpenTelemetry is not going to provide a dedicated logging API. Instead, support for existing logging libraries is planned. Most of them could have an OpenTelemetry appender assigned, which will correlate logs and send them through OTLP to the collector, concurrently using any other appender, such as console one. There is also support for injecting context into logs using other means, such as MDC for Java. If you want to send logs for using OpenTelemetry, I would say that right now, the best solution is probably to send them to some file and use file log receiver of OpenTelemetry collector. Support for native or support for logs in specific libraries is planned for the coming months, but I believe it's not there yet. And here, let's discuss about OpenTelemetry collector. This is one of these items that is required to make things work. OpenTelemetry collector can be largely thought of as a pipeline engine. We have separate pipelines for metrics, traces, and logs defined. Each of the pipeline can refer to a set of receivers, processors, and exporters. The purpose of which is, I think, particularly receivers get some data, processors modify the data, and exporters export data to some external service, like backend or maybe to file or so on. Here's an example of a very popular receiver, OTLP receiver. We can define that it will support, for example, gRPC and HTTP protocols, and there are some other configuration options available. Here is an example of one of the processors. In this case, this is configuration of attributes processor, which is a pretty complex one, I would say. Attributes processor allows to insert, update, observe, delete attributes at a given for given traces or logs at the record level. And here's an example of a simple exporter, in this case, gRPC exporter, which looks pretty similar actually to OTLP receiver, except you need to provide endpoint and some additional properties on what to do when exporting data. Here's a full example of a minimal config that provides two pipelines, traces and metrics. It's using OTel receiver for both traces and metrics. And for the exporter, it's using logging exporter. Logging exporter is a very handy tool in OpenTelemetry that sends all data to console so you can quickly check or debug what's going on with your data. It's very nice to see that the data is flowing and everything works as anticipated. And there are two OpenTelemetry collector flavors. One is core, and the other is contrib. Core contains the critical set of capabilities that are allowing to send and process and export data, build pipelines, and so on. It also includes some of the receivers and exporters. For example, OTel receiver and exporter is being included there. Contrib contains most of the processors that provide all these complex capabilities for enrichment, for transformations, and so on. Also, Contrib contains vendor-specific receivers and exporters, as well as receivers and exporters for other open standards. Additionally, there's an interesting project called OpenTelemetry Collector Builder. Builder allows one to very easily refer to specific modules in OpenTelemetry Collector, so one can have their own distribution that includes only the things that are required for the given use case. Additionally, vendors frequently provide their own distros, which are based on OpenTelemetry Collector. For example, there's a AWS distro for OpenTelemetry, and there's SumoLogic OpenTelemetry Collector and other vendor distros available. Additionally, there are some projects that make it easier in the cloud environment. For example, we have Helm chart, we have Kubernetes operator, there are Lambda extensions, and some other initiatives within OpenTelemetry. One of the greatest things about OpenTelemetry, I would argue, is community. It's backed by both individual contributors as well as people working for organizations such as Google, Microsoft, New Relic, Datadog, Splunk, Lightstep, SumoLogic, and many others supporting OpenTelemetry initiative. We communicate over a number of channels such as GitHub, CNCF, Slack, SIG, Zoom meetings, and so on. Everything is kept very transparent. There are meeting notes and recordings, which you can check out from each of the SIG meetings. There is a good number of detail of how this works on the community page, which I think is worth checking. And anyone can easily check the calendar. If there's anything they would like to discuss, they can join the meeting or discuss anything on Slack. As I mentioned, there's a lot of traction. Each of the repos has a good amount of things going on. Here's an excerpt from PRs to OpenTelemetry specification a couple of days ago. There's a dozen of them just during the last couple of days. And it's a similar story for other repos where iterations are happening quickly and project is moving forward. Another way to attest that is by looking at the peak at the CNCF stats. For several months already, OpenTelemetry is holding the status of the second most active CNCF project after Kubernetes. I think that this is another proof that the initiative is thriving, and it's worth using and contributing it, which I highly encourage. The community is very supportive. If you would like to contribute and there's nothing specific you want to add, but just you want to help, it's good to go through issues labeled as help wanted or good first issue. On the right side, there's a screenshot with some of those issues for OpenTelemetry Java project. Frequently, it's enough to just leave a note that you would like to start working on a given issue. And if the scope is huge, it's good to split this PR into several smaller PRs. One can include interface changes, the other implementation, and the final one, enablement of the future. Specific instructions on contributing are available at each of the repos. Please read it as well as the overall guidelines. And each contributor needs to have the contributor license agreement or CLA signed before the first comment gets accepted. It sounds scary, but it's a simple process described in the documentation. And this, I think, concludes my talk. Thank you for listening. I believe we now head to Q&A session. I will be more than happy to answer any questions you have. Also, you can reach me offline on LinkedIn. If you would like to contribute to OpenTelemetry, I think that this is a great idea. And if I can help, just reach out to me. Thank you.